Electronics for Dummies, a reference for the rest of us. About author Gordon McCobb has penned 60 books and over 1,000 magazine articles. More than 1 million copies of his books are in print in over a dozen languages. For 13 years, Gordon wrote a weekly syndicated newspaper column on personal computers. When not writing about hobby electronics and other fun topics, he serves as a consultant on digital cinema to several notable Hollywood clients. Earl Boyson is an engineer who, after 20 years in the computer chip industry, decided to slow down and move to a quiet town in Washington. Earl lives in a house he built with a wonderful lady and finds that he is as busy as ever with teaching, writing, house building, and acting. Contents. Introduction. Are you thinking about building your own electrical gizmo? Ever wonder how transistors, capacitors, and other building blocks of electronics work? Do you have an interest in finding out how to solder or make your own circuit board? Well, you've come to the right place. Electronics for Dummies is the key that opens the fun and exciting door to modern electronics. No dry and boring tome. What you hold in your hand is a book that gives you just what you need to know to make and troubleshoot your own electronic gadgets. Why buy this book? Electronics is make that huge subject. Like any science, it consists of a lot of concepts and all sorts of highly complicated mathematical equations. For any really in-depth study of electronics, you need to spend hours and hours memorizing a lot of facts and figures. But this book takes a different path. It provides you with just what you need to understand the basics of electronics. Get to work building circuits, and even tackle a dozen fun projects that you can build in under an hour each for just a few dollars. This book doesn't pretend to answer all your questions about electronics, but it does give you a good grounding in the essentials and make this exciting science fun. Why electronics? This is a rhetorical question because you no doubt already know why you have an interest in electronics, or you wouldn't have picked up this book. But we'll take a moment to review the things that make electronics worthwhile. First off, electronics is fun. You get to build things that beep, weird flashlights, and even move around the room. You acquire skills so that you can work with neat tools and proudly hold your head up at any gathering of electronic geeks. And don't forget that electronic products are all around us. They make up a growing part of our lives. Some people are content just accepting these gadgets, gizmos, and widgets, but others want to know how they work. Obviously, you're in the group, which is definitely the cooler group out there. The science of electronics have advanced to the point that you can now hold a very powerful computer in the palm of your hands. With that computer, you can build something that controls the lighting in your entire house. A robot that vacuums the living room all on its own. A sensor system that sounds an alarm. If somebody tries to get at your collection of 50s comic books, here's the amazing part. You can make electronic gadgets that do these things for just a couple bucks. At the same time that the art and science of electronics is rapidly advancing, the price of building a circuit that can do something incredibly nifty is dropping like a stone. Unless you're constructing a time machine or the world's largest robotic rabbit, the typical home-brewed electronics project costs little less than dinner for four at No Frills restaurant. If you're looking for a cool hobby, electronics is one of the least expensive ways around. Oh, and did I mention that electronics is fun? You may want to consider the possibility. People who know the practical side of electronics, that what things are, how they work, and how to put them together, can find some really great jobs on the market right now. If you're interested in a career in electronics, make this book your first step into the fun and rewarding new job. Also, many other hobbies rely on knowledge of electronics in some way. Maybe you're into modeling railroading. You can figure out how to build your own automated track switchers, or perhaps you like racing radio controls, parts with an understanding of electronics. You may discover how to improve the performance of your car and beat your best friend in the next race. Knowing more about how electronics works can make your other hobbies more fun. And last but not least, electronics is fun, or maybe I mentioned that already. Foolish assumptions. This book assumes that you know diddly about electronics. For the very first chapter, we introduce you to basic concepts that you need to master in order to follow what we say in later chapters. But if you already have a handle on the basics, you can easily jump into a later chapter and drive right in. If you need to know something really important to keep you safe from something such as an electrocution, we provide a cross-reference to send you back to the relevant chapter for a refresher course. You can also use the most excellent table of contents in the front of the book, an index that Wiley has thoughtfully provided at the back to quickly find information. Safety number one. Safety first is for number one. Safety is number one. Reading about electronics is pretty safe. About the worst that can happen is you get tired for too many late nights with this book. But actually, building electronic projects is another matter. Lurking behind the fun of the electronics hobby are high voltages that can electrocute you, soldering irons that can burn you, and little bits of wire that can fly into your eye when you snip them off with sharp cutters. Ouch. Safety is numero uno in electronics. It's so important, in fact, that we devote an entire chapter of this book, chapter 2, to it. If you are brand new to electronics, please be sure to read this chapter. Don't skip over it, even if you think you're the safest person on earth. Even if you've dabbled in electronics before, it never hurts to refresh your memory, your safety memory. When you follow proper precautions, electronics is very safe and the same insane hobby. Be sure to keep it that way. Although we try to give you great advice about safety throughout, we can't possibly give you every safety precaution in the world in one book. In addition to reading our advice, use your own common sense. Read manufacturer's instructions of parts and tools that you work with, and always stay alert how this book is organized. Electronics for Dummies is organized so that you can quickly find, read, and understand the information that you want. It is also organized so that if you have some experience with electronics, you can skip the chapter and move on to the parts that interest you. The chapters in this book are divided into parts that also help you find the information that you're looking for quickly and easily. Part 1, getting started with electronics. Start with this part if you're brand spanking new to electronics, because this book is designed to get you on the road to electronics as quickly as possible. This part has only 2 chapters, an overall introduction to electronic concepts and safety information. Please read Chapter 2, keeping humans and gadgets safe. If you decided to keep the introduction to electronics, you find in Chapter 1, Part II. Article 5, Component Shack Stocking Up. If you're just starting out in electronics, you probably need a couple tools. Read the most important ones in Chapter 3, Outfitting Your Electronic Bench. You can't make a project out of thin air. You need resistors, diodes, capacitors, and other building blocks for today's electronics. Chapter 4 and 5 explain what each of most important electronic components does and how often you use each in building circuits. Part III, Putting it on paper. If you've ever seen an electronic diagram, you probably thought it looked like an Egyptian hieroglyph. In Chapter 6, we explain all about how to read these diagrams. They're called schematics, and you can discover how to follow a schematic to determine the basic functionality of a circuit in Chapter 7. Chapter IV, Getting Your Hands Dirty. At this point, you're already ready to start building your own electronic projects. The chapters in Part IV tell you how to solder and how to use 3 of the most important testing tools in electronics: the multimeter, logic probe, and oscilloscope. You don't absolutely need the last 2 to get started with electronics, so you can come back to Chapter 10 a few months from now if you're just starting out. Part V, the plethora of projects. In Chapter 11 and 12, we demonstrate how to build your own circuits. We cover how to construct temporary circuits on something called a solderless breadboard. Then you discover how to produce permanent circuits using several methods, or by designing and ordering printed circuit boards from supply. Chapter 13 introduces you to the exciting new universe of microcontrollers, electronic circuits that you can program to do any of a million things. And finally, in Chapter 14 and 15, you can play with over a dozen fun and not too complicated projects that you can build yourself. So it says VI, the part of tens. This part contains several chapters laid out in top 10 list format. Here you explore some optional testing tools that you can add to your electronic bench. As you gain more experience, get advice about where to find electronic parts, finally study useful electronic formulas that don't require a degree in math. Icons used in this book. We're a graphical society, bombarded with images and blockbuster movies and computer games, and so this book uses little graphic icons to visually point out useful information that you may want to know. The tip icon indicates information that may help save you some time, headaches, or money, or all 3. These icons tend to point out tasty morsels that make electronics more enjoyable, so don't skip them. Something bad is about to happen. If you don't read the text about the following that follows the warning icon, that is, some of these points point out caution to avoid personal injury, and others give you advice on avoiding damage to tools, component circuits, or your pocketbook. Think to remember icons as a gentle nudge about important ideas or facts that you really should keep in mind while exploring the electronics world. We also use these icons to note where in the book some subject is originally introduced, so you can flip back to those chapters for a refresher if you need one. Part 1, Getting Started in Electronics. In this part, you say you've always wanted to get into electronics but didn't know where to start. You've come to the right place. In this chapter, in the chapter ahead, we cover the very basic of electronics and electrons and electronics, what they're all about and why you should care. But don't worry, you won't get bored to tears with some long essay on science and physics. We make the concepts and lingo easy to understand. Plus, in this part, you'll find some great tips on safety. Electronics is fun, but only if you don't get burned, electrocuted, or poked in the eye by a wild resistor. From electrons to electronics, understanding the role of electrons, conductors, and voltage. Looking at how electricity is generated, exploring some electronic components, connecting components together in circuits, introducing a few tools of electronic trade, breaking it all down into units, understanding the Ohm's law. When you plug in the coffee maker in the morning, you're using electricity. You flip on the TV to watch a rerun of Sex and the City, you're using electricity. For better or worse. Do you use electricity and electronic devices all the time? You finally worked up enough curiosity to want to tinker with electronic gadgets yourself. That's great, but before you can jump into playing with wires and batteries, it helps to understand what puts electricity in electronics. In this first chapter, you discover all about how electronics make electricity and how harnessing that electricity is the basis of electronics. You also get an introduction to some of the tools and parts that you can play with in electronics projects. In chapter 14 and 15, just what is electricity? Like most things in life, electricity is more complex than you may think. A lot of conditions have to come together to make that little spark when you touch a doorknob to provide the power to run a supercomputer. To understand how electricity works, it helps to break it down into parts. Let's break it down. First, you take an electron. Electrons are one of the building blocks of nature. Electrons are buddies with another of nature's building blocks. Protons. Electrons and protons are very small and are contained in, well, everything. A speck of dust contains millions and millions of electrons and protons, so you can imagine how many there are in your average sumo wrestler. So can you imagine how many there are in your average sumo wrestler? Electrons and protons have equal and opposite electric charge, with electrons having the negative charge and protons having positive. Opposite charges are attracted to each other. You can visualize a similar type of attraction by putting the ends of two magnets together. If the ends of the magnets are opposite poles, the magnets closely ride up to each other and stick together. If the ends of the magnets are the same poles, the magnets will move apart, like two politicians in a heated debate. In a similar way, because electrons and protons have opposite charge, they are attracted to each other, just as you can see opposite magnetic poles attracting. The attraction between electrons and protons acts like glue on a microscopic scale. Hold matter together. Although protons stay reasonably static, electrons and are adventurous little fellows who don't like to just sit around them. They can and often do move from one object to another, walk across a carpet on a dry day, and touch a doorknob. Electrons traveling between your finger and the doorknob cause that spark you feel and sometimes see. Lightning is another example of electrons traveling between two things, in this case between a cloud and the ground. These examples both show electricity in an unharnessed state, moving electrons around through conductors. What do electrons use to travel from one place to another? The answer to that question gives you the next piece of the electricity puzzle. Although you may use your old Chevy to get around, electrons use something called a conductor. Electricity is simply the movement of electrons through a conductor. A lot of materials can act as conductors, but some are much better at it than others. Electrons can move easily through metal, than through plastic. In plastic, even though all electrons are moving around their proton buddies, they are pretty much in their own backyard. But in metal, the electrons are free to move all over the place. Free electrons in metals act like marbles thrown on an ice skating rink. The electrons glide through the metal like the marbles slide across the ice. Plastic and insulator is more like sand. Marbles don't go too much of anywhere if you throw them into a sandbox, and neither do electrons in an insulator. So which materials are good conductors and which are good insulators? Most folks use copper and aluminum as conductors. In fact, electronics products often use copper wire conductors. Plastic and glass are commonly used insulators. Resistance is the measurement of ability of electronics to move through a material. A copper wire with a large diameter has lower resistance to the flow of electrons than a copper wire with smaller diameter. You need to understand resistance because almost every electronics project you do involves a resistor. Resistors have controlled amounts of resistance, which allows you to control the flow of electrons in circuits. Voltage, the driving force. The previous section in this chapter explains how electrons move and that they move more freely in a conductor. But some kind of force has to pull the electrons from one place to another. This attractive force between positive and negative charge is an electromotive force called voltage. Negative electrons move towards a positive voltage by way of conductor. Remember Anne Franklin's adventure flying a kite in the storm? The spark he produced that night gave him an understanding of how an electric current moves. In Ben's case, electrons traveled down the wet string, which acted as a conductor. This was at least in part because the string was wet. Try this same stunt with dry string, and it doesn't work nearly as well. The voltage difference between the negatively charged clouds and the ground pulled the electrons down the wet stream. Don't try Ben Franklin's experiments at yourself. By flying a kite in a storm, you are basically playing with lightning, which can effectively turn you into toast. What happened to protons? You may have noticed that we stopped talking about protons, although you should understand the positive and negative charge in protons and electrons. We're focusing on electrons because they're more mobile than protons. In most cases, it is electrons and their negative charge that moves through conductors that generate electricity. But in special cases, such as batteries, positive charge also move through conductors. To explain this process, you also have to get into things called ions, atoms, electrochemical reactions, and maybe even the concept of holes as used in semiconductors physics, because you don't need to understand these concepts to complete the projects shown in this book or most hobbyist level projects. Well, leave the most complex physics to Einstein and keep your focus on electrons. Conventional current versus real current. Early experimenters believed that electric current was the flow of positive charges, so they described electric current as the flow of positive charge from the positive to negative voltage. Much later, experimenters discovered electronics as determined that the flow of electrons in wires goes from negative to positive voltage. The original convention is still with us today. So the standard is to depict the direction of electric current in diagrams with an arrow that points opposite to the direction that electrons actually flow. Conventional current is the flow of positive charge from positive to negative voltage and is just the reverse of the real current. An important combo: electrons, conductors, and voltage. Say that you have a wire, a conductor, and you attach one of its ends to the positive terminal of a battery and the other end of the wire to the negative terminal of the battery. Electrons then flow through the wire from the negative to the positive terminal. This flow of electrons is referred to as an electric current. When you combine electrons to a conductor and voltage, you create an electric current. To help you picture how conductors and voltage affect the flow of electric current in a wire, think of how water pressure and pipe diameter affect the flow of water through a pipe. Here's how this analogy works. Increased water pressure causes more water to flow through the pipe. This analogous is increasing voltage, which causes more electrons to flow, producing greater electric current. Using larger diameter pipes allows more water to flow through the pipe for a given amount of pressure. This analogous to wire with a larger diameter, which allows more electrons to flow for a given voltage, producing greater electric current. Where do you get electricity? Electricity is created when voltage pulls an electric current through a conductor, but when you sit down and run wire between a switch and the light, just where do you get the electricity to power that light? There are many different sources of electricity, everything from walking across a carpet and touching a doorknob kind to solar power. But to make your life simple, this book takes a look at the three sources that you're likely to get your electric project: battery, your outlet, and solar cells. They just keep on going. Batteries. A battery uses a process called electrochemical reaction to produce a positive voltage at one terminal and a negative voltage at the other terminal. The battery creates these charges by placing two different metals in a certain type of chemical. Because this isn't a chemistry book, we don't get into the guts of a battery here. But trust us, this is essential. This is essentially what goes on. Batteries have two terminals. The terminal is just a fancy word for a piece of metal to which you can hook up wires. You often use batteries to supply electricity to devices that are portable, such as a flashlight. In the flashlight, the bulb has two wires running to the battery, one to each terminal. What happens next? Something like this. Voltage pulls electrons through the wire from the negative terminal to the battery to the positive terminal. The electrons moving through the wire pass through the wire filament in the light bulb, causing the bulb to light up. Because the electrons move in only one direction from the negative terminal through the wires to the positive terminal, the electric current generated by a battery is called direct current, or DC. This is in contrast to alternating current, AC, which is discussed in the following section. Garden variety electrical outlets. The wires on a battery must connect to both terminals. This setup allows electrons to flow from one terminal of the battery through the bulb and all the way to the other terminal. If the electrons can't compete this kind of loop between negative and positive, electrons don't flow. Garden variety electronics. When you plug a light into an electrical outlet in your wall, you're using electricity that originated at a generating plant. That plant may be located at a dam or come from another power source, such as nuclear power, or it may be fired by coal or natural gas. Because of the way electricity is generated at a power plant, the direction in which the electrons flow changes 120 times a second, making a complete turnaround 60 times a second. This change in electron flow is called alternating current, or AC. When the charge in electrons flow makes a complete loop, it's called a cycle. The number of cycles per second in alternating current is measured by Hertz, abbreviated Hc. The example of a cycle in the previous paragraph is based on the fact that the United States uses 60 Hertz standard frequency. Some other countries use 50 Hertz as a standard, which means the electrons change direction 100 times a second. Electricity generated at a dam uses water to turn a coil of wires inside a huge magnet. One of the properties of magnets and wires is that when you move a wire near a magnet, a flow of electrons is induced in the wire. First, the magnet causes the electrons to flow in one direction, and then when the wire loop rotates 180 degrees, the magnet pulls the electrons in the other direction. This rotation creates alternating current. Just plugging a cord into a wall outlet sounds easy enough, but you need direct current for most projects rather than alternating current. If you use wall outlets to supply electricity for your project, you have to convert the electricity from AC to DC. You can do this conversion with something called a power supply. For an example of a power supply. Think of a charger that you use for your cell phone. This little device essentially converts AC power into DC power. That power that the battery uses to charge itself back up. You can find out more about power supplies in Chapter 3. Safety. It's important. It's an important issue for you to consider when deciding whether to use the AC electricity that you get from wall outlets. Using the electricity from a battery is like petting a house cat. Using the electricity from a wall outlet is more like cozying up a hungry lion. With a cute tabby, you may get your hand scratched. With the king of the jungle, you may be eaten alive. If you think that you need to use electricity from a wall outlet for a project, make sure that you know what you're doing first. See Chapter 2 for specific advice about safety. Which came first, voltage or current? Batteries produce a voltage that drives an electrical current. Electric current. Generators at dams drive a current that produces a voltage. Which comes first? This is like asking yourself the well-known question about the chicken and egg. Voltage, currents, and conductors all work together. If there is a voltage applied across a conductor, electric current flows. If you have an electric current flowing through a conductor, there will be voltage across the conductor. Bottom line, don't worry about which comes first. Bottom line, don't worry about which comes first. Simple choice, AC or DC. What difference does it make if you use alternating or direct current? A lot of differences. AC costs less to generate and send over transmission line than DC. That's why you use AC for many household electricity needs, such as powering light bulbs and heaters. However, DC is simpler to use for projects discussed in this book, and many other electronic appliance applications. It's just plain harder to control AC current because you don't know which way it's headed. At any point in time, it's the difference between controlling traffic on a two-way 6-lane highway and controlling traffic on a one-lane, one-way street. So most of the circuits you read about in this book use direct current. Solar cells are a form of semiconductor. Like battery, solar cells have wires attached to the terminals. Shining light on a solar cell causes the electric current to flow. This reaction to light is a property of semiconductors and is discussed in the sidebar, Getting Fancy with Semiconductors. Later in this chapter, the current is then conducted through wires to devices, such as a calculator or a garden light decides the pathway to your front door. Using a calculator containing a solar cell, you can demonstrate that the calculator depends on the light shining on the solar cell for its power. Turn the calculator on and punch some numbers into the screen. Choose a nice big number like your income tax. Now use your thumb to cover the solar cell. The solar cell is probably near the top of the calculator in a rectangular area with a clear plastic cover. After you've covered up the solar cell for a moment, the numbers fade away. Take your thumb off the solar cell and the numbers reappear. Things provided by solar cells need light to work. Things powered by solar cells need light to work. Where do electric components fit in? Electric components are parts you use in electronics projects. Simple enough, right? You use some electrical components to control the flow of electricity, such as a dimmer switch that adjusts the brightness on a light. Electricity simply powers other electrical components, such as speakers blasting out sound. Still, other electronic components called sensors detect something such as light or heat, and then generate a current to do something in response, such as set off an alarm. In this section, you meet some basic electrical components. Chapter 4 and 5 provide much more detail about components. Controlling electricity. Electrical components are parts can control electricity. For example, a switch connects a light bulb to electric current to disconnect the light bulb and make it go dark. The switch simply makes a break in the circuit. Some other parts that control electricity are resistors, capacitors, diodes, and transistors. You can find more information on these parts in Chapter 4, Controlling Electricity Even Better. Integrated circuits, or ICs, are components that contain a whole bunch of miniature components, such as resistors, transistors, or diodes, which you hear about in Chapter 4. In one device that may not be bigger than an individual component because the IC contains many components. One little IC can do the same job as several individual parts. Getting fancy with semiconductors. Transistors, diodes, LEDs, integrated circuits, and many other electronic devices use a semiconductor. Instead of a conductor, a semiconductor is a material such as silicone that has some of the properties of both conductors and insulators. Silicone is pretty cool stuff. In fact, they've named a whole valley in California after it. In its pure state, silicone conducts an electric current poorly. But if you add contaminants such as boron or phosphorus to silicone, it conducts. When you add phosphorus, silicone becomes N-type semiconductor. When you add boron, silicone becomes P-type semiconductor. An N-type semiconductor has more electrons than a pure semiconductor. And an A-type semiconductor has fewer electrons than a pure semiconductor. When the regions containing boron and phosphorus are next to each other, in silicone, you have a PN junction. Current flows in only one direction across a PN junction. Diodes, components that can convert AC to DC by limiting the flow of current to one direction, are an example of components that contain PN junction. A PN junction generates an electric current when exposed to light. This property is used when building solar cells. On the other hand, when you run an electric current through a p-n junction, it emits light as light emitting diodes, LEDs do. Transistors use junctions in which three adjacent areas have contaminants added. For example, one region with phosphorus, one with boron, and the other with another with phosphorus results in NPN junction. In a transistor, you apply a current to the middle of the three regions, the base allowing a current to flow. Most electronics projects you work on use components such as transistors, diodes, and integrated circuits, and these are made with semiconductors. It's semiconductors that have made possible much tinier electronic gadgets like household computers and palm-sized radios.